Hi, everyone. Yeah, thank you once again for attending our webinar. And let me just share my screen. Okay, so it's we are now at 1:30. So right at the dot. Let's just start the webinar. So today webinar will be about safe underground transfer wall design from ETABS to IDEA StatiCa. I'll cover why we need to actually transfer the model from ETABS or any other global FA software to IDEA StatiCa so that we can more thoroughly check and design the wall itself. And I'll also show you a live demonstration of how to do it and to transfer the model from ETABS to IDEA StatiCa, and also modeling of rebars, and also how to read the design result and how to create a report in IDEA StatiCa Detail. Right, before starting, so my name is Stefano Kusumali. I'll be the presenter for today. I'm a product development engineer in IDEA StatiCa APAC. My background is about 5 years working in a design consultancy firm. Normally, I'll be designing underground structures and also some building superstructures. Right, so just a reminder that in this webinar, you are muted by default. So if you have any queries, if you have any suggestion or anything, you can always type it in this question panel here. Then we will get back to you either via chat or at the end of the webinar, where I'll be answering some of the interesting questions. Yeah, so don't hesitate to ask or give us any suggestion, if any. So before starting, I'll just turn off my webcam. So yeah, you can see my content in full view. And before starting the webinar, I have one poll. We would like to understand, how do you normally or currently design a transfer wall? Oof. Okay, sorry, I was not haven't clicked share my screen. Okay, so yeah, so for the first poll, right, before we start, we would like to understand, how do you normally currently design a transfer wall? Is it by a hand calculation straight and time method, or check in the global FEA, or do you use IDEA StatiCa Detail currently, or you don't design a transfer wall at all? So I just launch the poll. Yep. I'll just give it a few seconds to actually let the responses coming in. Okay, good result. Most of you will be checking a stress in the global FEA software. Interesting. And yeah, about 20% is using the well-known method, which is the strut and tie method. Right. Good. So far, so good. I'll just give it a last 10 seconds for those who haven't voted. Yeah, please give in your vote so we can understand better what is the situation on the market currently. Okay. Let me just close the poll. Yep, and I will share the result. Right, so yeah, interestingly, 27% and another 27% don't design transfer wall. The other 27% is actually using hand calculation and stress and time method. But the majority, 46%, is actually checking the stresses in a global FEA software. Okay, that's interesting. That's exactly why what I want to show you in this webinar, that actually checking a stress in a global FEA software might not be sufficient. Right, let me just continue my presentation. So yeah, so firstly, what is the case study for my demonstration today? So there is this building which has 3 level of basement and normal looking superstructures. But then when they are going into a more detailed design, they found out that there's some kind of a piping or a tunnel going under the building. If we see it from the top, it'll be something like this, right? So what's the consequence of this, right? For first of all, the basement on this side, yeah, we cannot actually build it. It was moved to this side. And then of course there are some impacted columns which they cannot do piling because underneath the column there is this obstruction, right? So yeah, this is the more isometric view. So these red color columns are the ones that are sitting on top of this obstruction. So it means that the engineers cannot actually do a piling underneath this column. So what idea do they have? They would just use a transfer wall to actually let those columns sit on this transfer wall, and then it will use these D-walls going down below as a foundation for these impacted columns. Right, so you can imagine that designing this massive transfer wall is quite scary and it's not easy. That's why I understand why some of you would be referring to the stresses in global FES software, especially if there are openings on them. I think it would be quite time consuming and quite difficult to build a strut and time model using hand calculation. That's why I understand why some of the engineers would choose to rely on a global FES software. Right. Okay, so yeah, just a short introduction of our software. Right, so basically IDEA StatiCa is comprises of steel and concrete modules, right? But for today, we are going to focus mostly on the concrete modules, which you can see on the right here, what we can solve, including anchoring, beam width opening, and pre-stressing and all that. Right, and then there are third, third application which we call checkboard. Okay, so why do I introduce this checkboard? Because checkboard is actually an application as a link between FES software into IDEA StatiCa, including IDEA StatiCa Detail. Right, so as you can see, ETABS is listed here. You can use checkboard to actually link it. And so I'm introducing this app because this will be the main, not the main, this will be the application that we use to transfer the data from ETABS to IDEA StatiCa Detail. Right, so yeah, as I mentioned, it'll be the model will be coming from ETABS, right? Then we will move it or transfer it to our application IDEA StatiCa checkboard before going into IDEA StatiCa Detail. Right. So actually, right, I want to talk about why do we need this this kind of workflow, right? So that's why on the next slide, I would like to introduce to you the concept of a B and a D region, right? So you can better understand what is the need to actually study this transfer wall in more detail in our application, IDEA StatiCa. Yeah, why is it even needed, right? Right, so what is this B and D region, right? B region is known as a Bernoulli or a beam region, right? This region is known to have a linear distribution of a strain. That's why it can be calculated from a well-known algorithm of formulas that you see inside the design code, design book, and all that. Right, so what is this? A B region is this region which is away from, let's say, a point load. It's away from the opening, it's away from changes in the section and all that, basically the yellow color one. This one you can just use the code, the formulas inside the code to do your calculation. Then what is this D region, right? This D region is actually those which we see in the gray color here. It's in the point load, near the point load, near the opening, you know, cover and all that. You can't just use a formula to actually design for this region. Why is that? Because this D region or discontinuity region is has a non-linear distribution of strain. That's why you cannot just use the formula. Like you would need to derive, let's say, a strut entire model. Like yeah, I think some of you are more familiar than me how to build this strut entire model. And yeah, so this is currently how to solve it lah. But of course, we IDEA StatiCa, we offer what we think is a better and more easier solution to use, and of course a faster solution to use, which is our application. So just to summarize the why, global FES software in itself is very good in overall analysis. That means it's a global analysis, global behavior and everything, and also in the B region, which means the beam, you know, the column and all that is very good, but it's not good in detailed analysis and D region, for example, like this coupling beam. Yeah, I think the global FEA will find it quite hard. Next, crack width is important for structures, right? It's the serviceability limit states. And particularly when we are talking about underground structures, right? That means, yeah, for particularly for structures that is in contact with soil, there are more stringent requirement to actually check and make sure that the crack doesn't pass certain limits lah. This one is done to prevent the corrosion of the rebar. But currently there's no way to verify this crack width using a hand calculation like strut and tie. It will only give you a ULS result, but not the SLS result. And also in your global FES software, you will not be able to find the crack width result. I'm talking about ETABS. For wall, you will not be able to find the crack width result. But of course, in IDEA StatiCa Detail, you can find this crack width result. As you can see here, one of the example of our output. And lastly, engineers want to do a detailed analysis of complex wall in IDEA StatiCa, but there was no link. That's why we created this link. So now we have it already. So last time you have to like remodel the model and put in your load, but since we now have it already, you don't have to do it all over again. So what are the use cases of IDEA StatiCa Detail? Would be, let's say, for coupling beam, you know, walls with opening, like this very complex walls, which you like, it's quite hard to build a strut and tie model out of this. And of course, our use case for today, which is a transfer wall. Then, yeah, lastly is the before the demo, there's let's say an example from one of our customer in Brazil. He was designing this wall which changes in the cross section, right? He do it in ETABS, but then he is not very sure in this area how the stress will go, how the rebar will, you know, how the rebar will act, what is the stress and all that. So that's why he actually modeled this particular structure inside IDEA StatiCa Detail to study the behavior in a more detailed manner. Right, so that's all the theoretical part or introduction part that I have. Now is going into a live demonstration part. But before that, yeah, there's another poll because we really would like to understand how is the market actually doing calculation in the crack width currently. So I'm going to just launch the poll. Right, so I just give it a few seconds for you to start answering the poll. So we would like to understand, how do you calculate crack width currently? Is it like approximation using stress, or is it like only ULS because you are using short and time method, right? So it's only ULS, you're checking on the ULS, or you are already using our software, or maybe you are using some other software. Right, so I just give it another few seconds. So yeah, for those who haven't voted, please, we would like to hear what you are currently using, and how is the market actually solving this problem. Right, I just give it the last 5 seconds, and yep. Okay, let me just close it and share the result. Right, so yeah, most of you will be designing only for ULS. That's understandable, because on the first polls, most engineers will be using stress and tie. Second one will be approximation using stress. Yes, this is also quite a common method. And 17% using other software. I'm wondering what software. And only 3% is using IDEA StatiCa Detail. So yeah, I think it's a good opportunity that I can introduce you to our software so that you can start using it. Right, so as for the demonstration, yeah, as I've described earlier, right, there'll be this building and there'll be this transfer wall. Just close my presentation, sorry for that. Okay, so let me just show all object. Wait, I hide the flaws. Right, so this is our buildings. You can see those 3 transfer wall there too. So you can see it more clearly. I just hide the superstructures. And I will also need to hide the flaws. Right. So as you can see, there are these 3 transfer wall, but for today, we will be focusing on this transfer wall here, which I have a model in more detail with some openings. So if I really run this model, if we go in more in the elevation view, so that you can see more clearly. Yep, and let me just let's say I finish running and I want to see whether my wall can work or not. I just use show the ULS principal stress, which is the principal compression stress, which is S min. So yeah, just a brief intro. ULS 1 is for the gravity load only, and ULS 2 is for the dead load plus uplift, because we are talking about underground structure, so there'll be some uplift. So I think the highest compression force will be from ULS 1. That's why I turn on ULS 1. And as you can see here, the most critical area will be at this near this opening. So if I zoom in, you can see that it is about 16 MPa around here. So let me just try if I can zoom it in a bit. Yep. Okay, so yeah, probably it's better for you to see that. Yeah, this is around 16 MPa. So if you are designing for a concrete of FCK of 30, right? Then there'll be some material safety factors. So the FCD, or the allowable stress for FC, will be 20 MPa. So if you see this, then you are referring only to the stress from the global FES software, then you will say that this is actually okay. Well, is it really okay, right? Well, depending on our analysis, we will see in our analysis and see if this is okay or not. But based on the global FES software stresses, it seems okay for now. So I want to study this wall in more detail. I will bring it to IDEA StatiCa Detail. how to do that. You go to tools here, right? There's this our plugin wrapper, or our link to open checkboard, which you can click, right? So once you click, checkboard will actually open on the side. Don't forget to change to project type of concrete, because we are designing concrete transfer wall. And then just click create project. Right. Yeah. Let me just, okay, cool. Okay, so this is still a blank screen because we haven't imported anything. So you just go back to ETABS, select whichever wall you want to import, select, then you just go back to a checkboard here. We just make it slightly bigger. And then click this wall import on the top left here. And I just finish importing. Once you have it here, you can see all the geometry is here. You can see that all the combos that I have shown you before is also automatically transferred. Then also, of course, the material and the wall thickness also automatically transferred. So once you are okay, check everything okay, then you click on this. Okay, you click on this detail here. Once you click this detail button, you select all the walls that you want to bring over to IDEA StatiCa Detail, then you right click. Once you do that, you have the option to merge wall, meaning all this separation that we did in ETABS will not be there anymore. We'll merge it to one wall, which is what I want. So you just right click to this and export, and click export to detail. Once you do that, just select where you want to save the detail file and then just put a file name. Then just click OK. Right, then it will automatically open our IDEA StatiCa Detail. Just give it a few seconds. It's opening on my other screen. Yep, still opening. Just give it a few seconds. Yep, I will bring it to my other screen once it's fully open. Okay, okay, it's opening directly at my main screen. Okay, that's good. Right, so yeah, as you can see here, the geometry is automatically transferred. Then, of course, all these loads you can see here is also automatically transferred over. This is will be the column load here. This will be the loads from the slab, all right? Live load as well, and also, of course, as I mentioned, because this is an underground, there'll be an uplift force coming from the base, the most bottom slab, or the base slab, as we usually call it. And lastly, there'll be a ration force coming from the pin, which we had in ETABS. Actually, this ration force is coming from the wall below this, right? Because in ETABS, we actually have this wall below our wall that we bring to IDEA StatiCa Detail. But this one we can just ignore because we will put a pin over there anyway, so that it'll be automatically transferred to the support. What else? Yeah, ULS combination, as I mentioned. Yeah, because we already create this in ETABS, it'll be automatically transferred over. So firstly, if we want to analyze our wall in IDEA StatiCa Detail, what we need to do is first to put in our rebar, input our rebar, right? Right, so let's just start by clicking this rebar assembly, group of bars. Then I'll just change the location by using this H, right? This is the H number. This is number 1. And this is number 7. I want to create the shear links for this D wall here. So I'll be using H number 8 here. H number 8. Then I change the anchorage because anchorage type will be a perfect bond because this is a shear links. Yeah, you will actually connect it to the main rebar. Then I'll change the number of bar in layers, meaning into the paper, I'll change it to 2 because I only want 2 layers of rebar. The number of layers I'll change to 40 so that you have the full length of the diaphragm wall here. Right, and next I want to create a main of vertical rebar for this D wall. Same as before, I'll change the H to H number 7 because as you can see, this is number 7. Then I'll change it to continuous bond below and yeah, this type of anchorage on top. Then the number of layers to 13. So you have something like this for the D wall. You'll have to do it again on the other side, of course, but I will not be doing it just to save some times. And I'm going to move on to put in some wall in the some rebar on the transfer wall. All right, so you can just copy it. Then yeah, I just change it to this type, and then H still number 7, but I want to move it in a little bit because I want to put it here. So I change to user value 250, and then the number of layers would be 6, right? Something like this, right? So you don't have to worry about this rebar going out because our software will smartly detect it and ignore it in the analysis. Then I'll just copy this again. And then I just move it in a little bit more, and then I change to 13. Yeah, so you can imagine you can do it again for the other side with different concrete cover. Yeah, so it is moving inside lah, sort of. And then I want to start putting in the vertical rebar for this region on top and below the opening. Just change diameter. Then change the cover again and just move it to the left right here. And then the number of layers will be 16. All right, but as you can see here, this one go through the whole opening, right? I don't want it. I only want on the top part above the opening. So you can actually change the length here by clicking this part H from the beginning, position 0, because yeah, you want to keep it here. Then the length I just put 2 meters. Right, and because this is a shear links, again, I put the anchorage as a perfect bond. That's all for, yeah, we do the same for all these other wall on top or below the opening, you know, and just shortly, yep. I just quickly do it. Yeah, so as you can see, it's very flexible. You can just move it around. Then you change number of layers depending on the length of this, this guy here. And then last one for the bottom one, yeah. Of course, the length should be changed to, okay, so all the vertical rebar is ready there. So what's left is only the horizontal rebar for this main part here. Just change the diameter back to 20. Then as before, I changed the H to number 6, right? Because here is number 6, we want a horizontal rebar. So we change to number 6. Right, then I want to position it from 0.5 and the length to be 14,600 millimeters or something like this. And yeah, I just changed the number of layers because 26 is not enough apparently. So I just changed to 33. Then don't forget to change the anchorage type. That's it. And as I mentioned before, for the diaphragm wall on this side, you can do the same operations as you did here. What is happening? Cannot be applied. Shit, it's not of the model. Okay, let me just retry it one more time. Okay, so it's the cover apparently. Okay, nice. So we have all this rebar, and as I mentioned, the diaphragm wall on this side, the rebar, you can just follow what operation that I did here. To save time, I won't be repeating that again. So what's left after the rebar would be the support, right? You just click on the model entity here. I want to put a line support. And as before, it will be asking for which edge you want to support. I put on edge number 8 here. I want to turn off compression only, and I want to put it as a roller on this side. Okay, and then I copy it, change the edge to number 4. And this one, I want to put a pin too, because to make it stable, it cannot be roller and roller, right? One of it has to be a pin. And I put a roller here just to be a conservative. This is a conservative assumption, of course. It's like when you are designing a strut and tie, you'll be using one pin and one roller. So likewise here, this is based on engineering judgment, I would say. But most of the engineers would be choosing to do it on the conservative side. I've prepared a model which already have rebar on the other diaphragm wall. So as you can see here, this will be the final rebar arrangement that you'll see. Once you are satisfied with everything, then there's no warning here. You can just click calculate on top here. But of course, to save time, as we have a very limited time here, I have prepared a result here. Right, so once you click calculate, this will be the result. So if we look back at our global analysis stress principle, compression stress value, this is 16 MPa, right? But when we bring it over to IDEA StatiCa Detail, we put all the rebar and everything. Actually, you see on the top left corner here is actually failing, both in ULS and SLS. So that's what we mean by it might not be sufficient if you only look at the compression or stress value inside your global FEA. Yeah, so this is what we meant by that. But then, of course, you will ask me why, right? It seems like 16 MPa is less than 20 MPa, correct? Well, if you want to check more detail, you go check the design result. You go to this our check tab here. Yeah, on top here there are a lot of options. The first one that you will automatically open is the summary. Okay, it just tell you what is the utilization here. So if you are looking at the utilization, or you can also see it on the top left here, the highest utilization is actually in concrete itself. So what does it tell us? Right, so actually is a concrete compression failure lah. Even though we have made sure that inside our global FEA is okay, but here concrete compression failure happened. Let's investigate in detail. We'll click this strength button because I want to actually see the what is the stresses, compression stresses that we analyze. So yeah, this is a stress versus divided by capacity, which is utilization. So as you can see, the highest utilization is as we expected. Same with ETABS in this area here near the opening. But what is the stress value, right? Let's just take a look at this sigma C. Right, so it's around actually 17 to 18, which is Well, you tell me that 18, 17, well, it's still below 20 MPa, right? Why is IDEA StatiCa say it fails? Is it like, something wrong with the software? Actually, no, right? Because we have this KC2 factor, right, which is compressive strength reduction factor. What is that? I'll explain in a bit, but once we click this KC2 button here, reduction factor, you can see that there's a reduction factor of about 0.87 here. So what does it mean? Well, your concrete capacity or design capacity 20 MPa will times this 0.87, so it comes out to about around 17-ish lah. So that's why when we touch 17, although it's less than the FCD or allowable design stress, it's already showing the utilization of nearing 100, which means it's already failing compression. So what is this compression reduction factor? Is it even considered in the code? Do we really have to consider this? The answer is yes, actually. So let me just move down. So what is this factor? Actually, this factor is to capture this phenomenon we call compression softening. When the concrete is under compression, there's a transverse tension, right? The perpendicular direction, there'll be transfer crack. Transfer crack means less confinement, weaker compression capacity, which means is a compression softening. So how does the building or design code consider this? If you see both the most popular design code will be Eurocode and ACI. If you see Eurocode, if you have a strut, you're doing strut and tie, there'll be a reduction factor of some reduction factor here. For this case is 0.6, but for other case is K2 and K3, which is of course less than 1. So you can see it's less than 1 times FCD. So it means your FCD or your allowable design stress will be reduced to a factor less than 1. Same in the ACI for different strut location, strut type, and criteria. There'll be this beta factor, they call it. Same as you can see here is actually less than 1, right? So 0.8, 0.6, 0.75, and all that. But in IDEA StatiCa Detail, you don't need to worry. You just need to put in everything, run the analysis, then this reduction factor will be automatically calculated. So that's the answer why, in our opinion, relying on the stress of the global FVA is not enough, because this stress reduction factor is not included. So how do you go about this, right? How do you solve this issue? Well, what I would do, right, I would just put a additional compression bar here, so that some of the stresses will actually go to the compression bar and not into the concrete. And also, yeah, also you can see there's a SLS failure here. I just want to see the crack width, right? As I mentioned, we also put out our crack width, output our crack width. Yeah, so as you can see, the crack width is around here, this area, because when this one go down or sag, then there'll be a tension force around here. And something like that. So to help to prevent this ULS failure and to prevent this crack, I will put a rebar over here, right? And also a diagonal rebar over here, diagonal compression rebar. I'll just skip the modeling part and just show you the result once we have this diagonal and I have this additional rebar here. So once I click calculate, you can see on the top left here, actually the ULS is already passing, left the SLS only. So I go to the check tab again. I just confirm what is going on inside my model. Why is it now passing? Now let's go click on the strength tab here. So as you can see now it's passing. Yeah, although it's a very high utilization, but it's actually already passing. Let's check if our compression rebar actually taking the compression stress. You can click on the reinforcement here. You can check the sigma S or the rebar stress. Red color indicates a compression. So as you can see here, this rebar actually helps the concrete take in some of the compression forces. That's why there's no more compression failure from the concrete. Then now let's check the crack width once again, because we had an issue. We still have an issue in the crack width. Yeah, so as you can see, there's still the same issue around the opening, but there's no more issue on the horizontal crack width here. So what does it tell us? It means that, well, your opening, you need to put in some, when you have an opening, normally you have some standard rebar around it to strengthen the openings. So I'll just put it in, because yeah, we haven't put a rebar around the opening. How to do it, right? This one I will model it. It's very simple actually. Just click on the rebar assembly here, and then you just put cages around the opening here. I just put it for O2 first, which is this one. You can actually define the same, like the diameter, the length, the rebar layer, distance, and all that. And I'll just do it like this, then 400, and yeah, something like this. If you really cannot see the rebar that you're modeling, right, you can actually turn off all other rebars by clicking this one here. Okay, once you have it, I just copy it, change to O3, which is this one. I just put the same standard rebar. And for the last one, I'll put a little bit more, because in my previous analysis, it will show failure. Okay, sorry. Then I'll change it to O4. So if you want to see all the rebar that you have just modeled, you can actually do multi-select, and yeah, that's it. Rebar around the opening. Then I'll just click run again, and yeah, we'll see the analysis result. Same like before, I've pre-prepared a model, right? So as you can see here, all the ULS is okay. SLS left with a failure in a stress limitation. So what is this, right? Why is this still a failure? You can go to the check tab again and go to stress limitations to actually check what is going on. Right. Yep. So you can see here, actually it's in the corners that are failing the stress limitation. So what is this? Just going back to my presentation again. Right, so this is called stress singularity, right? So all FEA-based software will have this issue, whereby there'll be change in the abrupt change in the cross section. On the corner nodes, they will have this so-called stress singularity. This is a property of a behavior of all FEA software out there, right? So for stress singularity, if you are sure this is stress singularity, then we can ignore it. That is different if it is a stress concentration. Stress concentration is a real behavior, or it's a real stress which is there. So for stress concentration, you cannot ignore it, and you must design for it. Then how do you differentiate between these two? Stress singularity usually happens in this like sharp corner. And if you actually make the mesh smaller or finer, for stress singularity, the stress value will go up super high. So if you make it even smaller, it will go to infinity. But for stress concentration, if you make the mesh finer, it will actually be around the same value. So that's when you know this is a stress concentration, not a stress singularity. So for that reason, I know that this is a stress singularity. I'll just click this limited check. So it means that I'll just ignore this stress singularity. So I'm satisfied with my design already. It's already passing everything. We just go see the crack width once again. All right, as I mentioned, the traditional calculation method such as strut and tie cannot provide this. But here you can really see where you're cracked and what is the direction of crack that is, that you are having. Yeah, so you can see everything. I've shown you concrete stress, rebar stress. You can also check anchorage, deflection. For example, if you are curious about your long-term deflection. As I mentioned, SLS2 is the uplift. That's why on the base slab is actually going up. This is quite useful to check whether the model is correct or not. Once you're satisfied, you can go to the report tab here to actually generate a report for your submission. Just click a generate button here. Okay, let me just generate it quickly for you. Yeah, I just continue my presentation first and then I'll get back to here. Right, so that's it for my demonstration part. And lastly, the is a verification, because we understand engineers' safety is important, right? So we do a quite thorough verification. We have several use tests here, test cases, I mean here, such as cobble, D-beams, and shovel way opening. Then we compare the result with a well-known method, which is what we all know is a STM or strut and tie method. Okay, and we also compare it with the measured load, which means we do a physical testing and then measure it, plot the capacity here, and then we measure it with our result. So as you can see here, IDEA StatiCa or CSFM on the orange color here is actually quite close, right? But it still have some buffer to the actual physical testing. Whereas strut and tie method is a bit lower, a bit more conservative for cobbles, a bit even more conservative for deep beams, but for shear wall way opening, you can see that actually STM capacity is super low compared to the physical testing itself. So what does it mean? If you are using IDEA StatiCa Detail, you can actually save some of the material, including rebar or concrete. You don't need that much concrete or rebar to actually design your wall, and it's actually still within the buffer of physical testing, so it's also safe, right? So to end everything is a summary of my my demonstration just now. Principal stress in global FA is minus 17.4. FCD is 20 MPa. If you are only looking at the global FA, it should be okay, right? But is it really okay when we are actually bringing it to our IDEA StatiCa Detail? Well, there's a failure, and we have to add additional compression rebar to alleviate or take some of the compressive stresses from the concrete into the compression rebar to allow the wall to work. So yeah, you are using IDEA StatiCa Detail. You can see concrete stresses, rebar stresses, crack width, even long-term deflection. So these two on the right, the SLS, as I mentioned before, will not or can't be provided by traditional hand calculation method. And we also have a quite extensive report. Yeah, okay, so it has finished loading the report. Has everything, including this so-called bill of material. Yeah. So when it comes to a construction, you don't need to derive or create another bill of material. Actually, everything is there already. Just need to submit this to your contractor. Right. So this is I find it very useful. Right. So extensive report and a nice bill of material for construction. Right, so final summary. why do we want to use IDEA StatiCa Detail? It's a better solution, both B and D region. So you don't need to separate again between B and D region. It's, as you can see, safe and secure compared to a physical testing, verified. Also, save time. It will be quite time consuming to derive to create a stride and time model. If the opening changes, then you'll have to create a new model. But in IDEA StatiCa Detail, you have to just move the opening and rerun the analysis. Lastly, there's a correct width which we can provide, not with the traditional hand calculation method. Second, as I mentioned before, is a saving in material, because CSFM or IDEA StatiCa Detail actually predicts capacity closer to reality. Yeah, this is what I meant before. If you are using STM, right, then the capacity will be very low, which means you will put in much more rebar and concrete into your design. Lastly, we have a link from ETABS to detail. So that means no data loss, no data error, and of course, save some time because yeah, you don't need to actually remodel the whole thing again. Right, lastly, before I close the presentation, the last poll, right? We want to hear from you if it's, yeah, if it's actually useful or not, the links, because we want to, you know, we want to make our development as, you know, as close to the market demand as possible, so that you can actually find it useful. So yeah, please please put in your votes so that we can align our development effort into what you guys want, so you guys have a better workflow in your daily work lah. Yeah, so is it very useful? Is it useful? Is it neutral, or is it no? Right? Because if it's no, then right, we won't spend quite an effort to develop this link even further. Right, but if you really find it very useful, then of course we will put some development effort to make your life easier lah. Right, so yeah, some of you has voted. Let me just give it a few more. I'll give it the last 10 seconds for those who haven't voted. We would like to hear what is your opinion. We would like to hear, yeah, what are your thoughts? Okay, then I'll just close the poll. Okay, I share the result. Okay, so grateful that yeah, majority find it very useful and the rest find it useful, right? So that's a quite good result. And yeah, so we, for this year, right, we have a webinar. We plan to have a webinar every month, right? So the next one will be on the 5th of March, design of connections for temporary structures. My colleague Jean will be talking about temporary structures, such as, you know, when you are having ERSS, there's a strutting, you know, then you will need to design for the connection. So if you are coming here today and you are designing underground structures, this will be quite an interesting topic for you, because my colleague will be also talking about connection in strutting. And then the next one, we have it in April, 2nd of April. Please, we have some topics on mind lah, but we would love to hear what you want to hear. So let us know what you want to hear in the survey after the webinar. Right. So I think that's it for today's webinar. Yeah, so once again, thank you very much for attending this webinar, and hopefully I can see you again in the next webinar in the 5th of March, right? Okay, then see you. Bye-bye. Thank you, everyone.